Good day to all of you. So we're already on the third chapter of William Stalling's Computer Organization and Architecture. So what is chapter 3 all about? So it is all about a top-level view of computer function and interconnection. So, at the top level, a computer consists of CPU or the central processing unit, memory, and I/O components or the input-output components, with one or more modules of each type. These components are interconnected in some fashion to achieve the basic function of the computer, which is to execute programs. Thus, at the top level, we can characterize a computer system with describing first the external behavior of each component, that is, the data and control signals that it exchanges with other components, and second, the interconnection structure and the controls required to manage the use of the interconnection structure. This top-level view of structure and function is important because of its explanatory power in understanding the nature of a computer. Equally important is its use to understand the increasingly complex issues of performance evaluation. A grasp of the top-level structure and function offers insight into system bottlenecks, alternate pathways, the magnitude of system failures if a component fails, and the ease of adding performance enhancements. In many cases, requirements for greater system power and fail-safe capabilities are being met by changing the design rather than merely increasing the speed and reliability of individual components. This chapter focuses on the basic structures used for computer component interconnections. As a background, the chapter begins with a brief examination of the basic components and their interface requirements. Then a functional overview is provided. We are then prepared to examine the use of buses to interconnect system components. So let's start the topic with computer components. So as discussed in chapter 2, virtually all contemporary computer designs are based on concepts developed by John von Neumann at the Institute for Advanced Studies in Princeton. Such a design is referred to as the von Neumann architecture and is based on three key concepts. First is the data and instructions are stored in a single read-write memory. Second, the contents of this memory are addressable by location without regard to the type of data contained there. And then execution occurs in a sequential function or unless explicitly modified from one instruction to the next. The reasoning behind this concept was discussed in chapter 2 but is worth summarizing here. There is a small set of basic logic components that can be combined in various ways to store binary data and perform arithmetic and logical operations on that data. If there is a particular computation to be performed, a configuration of logic components designed specifically for that computation could be constructed. We can think of the process of connecting the various components in the desired configuration as a form of programming. So the resulting quote-unquote program is in the form of hardware and is termed a hardwired program. So let's differentiate the hardwired program and the soft-wired program in the term. So we have this figure 3.1. We have the hardware and software approaches. We can see 3.1a, which is programming in hardware, and we have 3.1b, programming in software. So now consider this alternative as already discussed in the previous slide about hardwired programming. Suppose we construct a general purpose configuration of arithmetic and logic functions. This set of hardware will perform various functions on data depending on control signals applied to the hardware. In the original case of customized hardware, the system accepts data and produces result as is simple with 3.1a. So for example, we need a sum, so we need addition function. So we have to rewire it for addition. So we have sequence of arithmetic and logic functions. What if we want to have an operation of subtraction? So since you've used and rewired this hardware in for addition, you need to change or rewire it for subtraction, for multiplication, or for division. Maybe the diagram is simpler because it only uses one step, or just a sequence of arithmetic and logic functions. So for 3.1a. So with B, with a general purpose hardware, the system accepts data and controls signals and produces results. Thus, instead of rewiring the hardware for each new program, the programmer merely needs to supply a new set of control signals. So, how shall control signals be supplied? The answer is simple but subtle. The entire program is actually a sequence of steps. At each step, some arithmetic or logical operations is performed on some data. For each step, a new set of control signals is needed. Let us provide a unique code for each possible set of control signals, and let us add to the general purpose hardware a segment that can accept a code and generate control signals. So for 3.1b, so we have it's like two steps. So first is what if we need um, addition for, and then the result is of course sum. So we have instruction codes for addition, and then of course instruction interpreter. So it interprets, oh, this is for addition, and then it will produce a control signal for addition, and it will be sent to the general purpose arithmetic and logic operations, and it of course it will apply the or adding two or more numbers because of the data, and the result is the sum. So for subtraction, it also goes with the same way. The instruction interpreter will interpret as a subtraction or multiplication or division. It will give control signals based on the arithmetic. This is just an example. For example, for subtraction, multiplication, and division, and it will be sent to the general purpose arithmetic and logic function for it to execute whatever it is needed. So instead of 3.1a, which is you need to rewire every time there is a new operation that is needed. Instead of that, which is very taxing, for this 3.1b programming in software, you don't need to rewire the computer components. So actually, 3.1b is easier to implement. So next, let's talk about software and input-output components. So because of 3.1b, programming is now much easier. Instead of rewiring the hardware for each new program, all we need to do is provide a new sequence of codes. Each code is, in effect, an instruction, and part of the hardware interprets each instruction and generates control signals. To distinguish this, a new method of programming, a sequence of code for instruction, is called a software. So for figure 3.1b indicates two major components of the system. So as we can already remember, we have first is the instruction interpreter and a module of general purpose arithmetic and logic functions. These two constitute the CPU, and then several other components are needed to yield a functioning computer. Data and instructions must be put into the system. For this, we need some sort of input module. So this module contains basic components for accepting data and instructions in some form and converting them into an internal form of signals usable by the system. A means of reporting results is needed, and this is in the form of an output module. Taken together, these are referred to as the I/O, or the input-output components. And then next is we have memory, all about memory, and then it's registers. So one more component is needed. An input device will bring instructions and data in sequentially. But a program is not invariably executed sequentially. It may jump around, such as the IAS jump instruction. Similarly, operations on data may require access to more than just one element at a time in a predetermined sequence. Thus, there must be a place to store temporarily both instructions and data. So that module is called memory or main memory to distinguish it from external storage or peripheral devices. Von Neumann pointed out that the same memory could be used to store both instructions and data. So the CPU exchanges data with memory. For this purpose, it typically makes use of two internal to the CPU registers, the memory address registers, or the MAR, which specifies the address in memory for the next read or write, and a memory buffer register or the MBR, which contains the data to be written into memory or receives the data read from memory. Similarly, an I/O address register or the IOAR specifies a particular I/O device, and then an I/O buffer or the IOBR register is used for the exchange of data between the I/O module and the CPU. So we have an illustration here in figure 3.2, the computer components in its top level view. So this figure illustrates these top level components and suggests the interactions among them. A memory module consists of a set of locations defined by sequentially numbered addresses. Each location contains a binary number that can be interpreted as either an instruction or data. An I/O module transfers data from external devices to CPU and memory and vice versa. It contains internal buffers for temporarily holding this data until they can be sent on. So another figure is we have figure 3.3, the basic instruction cycle. So as you can see, we have the fetch and execution cycle as part of the instruction cycle. So the fetch and execute cycle. So the basic function performed by a computer is execution of a program, which consists of a set of instructions stored in memory. The processor does the actual work by executing instructions specified in the program. This section provides an overview of the key elements of program execution. In its simplest form, instruction processing consists of two steps. The processor reads or fetches instructions from memory one at a time and executes its instruction. So program execution consists of repeating the process of instruction fetch and instruction execution. To illustrate that, so we have this fetch next instruction. Then after fetching the instruction is we need to execute that instruction, and then we have to repeat it until all of the needed instructions are already executed, and then it will come to a halt. And then we have the instruction execution may involve several operations and depends on the nature of the instruction, such as um, we have as you can remember in figure 2.4 in the last chapter. So the processing required for a single instruction is called an instruction cycle. Using the simplified two-step description given previously, the instruction cycle is depicted in this figure 3.3. The two steps are referred to as the fetch cycle, as I have already mentioned, and the execute cycle. Program execution halts only if the machine is turned off. So the status of the program execution, if of course the computer is off, some sort of unrecoverable error occurs, or a program instruction that halts the computer is encountered. Okay, so we're going to talk about this two parts of instruction cycle. So we have first is the fetch cycle. At the beginning of each instruction cycle, the processor fetches an instruction from memory. In a typical processor, a register called the program counter or the PC holds the address of the instruction to be fetched next. Unless told otherwise, the processor always increments the PC after each instruction fetch so that it will fetch the next instruction in sequence, such as the instruction located at the next higher memory address. So, for example, consider a computer in which each instruction occupies one 16-bit word of memory. Assume that the program counter is set to memory location 300, where the location address refers to a 16-bit word. The processor will next fetch the instruction at location 300 or 300. On succeeding instruction cycles, it will fetch instructions from locations 301, 302, 303, and so on. So this sequence may be altered as explained presently. So the fetch instruction is loaded into a register in the processor known as the instruction register or the IR. The instruction contains bits that specify the action that the processor is to take. The processor interprets the instruction and performs the required action. So what are these actions? So on the next slide is we have the action categories. So in general, these actions fall into four categories. First is we have the processor memory. Data may be transferred from processor to memory or from memory to processor. And then we have another one, processor to I/O or processor dash I/O. Data may be transferred to or from a peripheral device by transferring between the processor and an I/O module. And then next is we have data processing. The processor may perform some arithmetic or logic operation on data. And then the fourth one is we have control. An instruction may specify that the sequence of execution be altered. For example, the processor may fetch an instruction from location 149, which specifies that the next instruction be from the location 182. They are not really sequentially in order. The processor will remember this fact by setting the program counter to 182. Thus, on the next fetch cycle, the instruction will be fetched from location 182 rather than 150, which is next for location 149. So an instruction's execution may involve a combination of these actions. So next is we have the figure 3.4, characteristics of a hypothetical machine. So we have 3.4a, we have the instruction format, 3.4b, we have the integer format, 3.4c is the internal CPU registers, and 3.4d are the partial list of opcodes. Consider a simple example using a hypothetical machine that includes the characteristics listed in this figure. The processor contains a single data register called an accumulator or AC. Both instructions and data are 16 bits long. Thus, it is convenient to organize memory using 16-bit words. The instruction format provides 4 bits for the opcode. So as we can see here, and then so that there can be as many as 2 raised to 4 is equal to 16 different opcodes. And of course, since this is 16-bit, 16 minus 4 is we have 12, so that the remaining is 2 raised to 12, which is equivalent to 4096 or 4 kilobyte words of memory that can be directly addressed. So another figure is we have an example in figure 3.5, example of program execution which contain contents of memory and registers in hexadecimal. So this figure illustrates a partial program execution showing the relevant portions of memory and processor registers. The program fragment shown adds the contents of the memory word at address 940 to the contents of the memory word at address 941 and stores the result in the later location. Three instructions, which can be described as 3 fetch and 3 execute cycles, are required. So first, the PC contains 300, as already can see this in this figure. The address of the first instruction. This instruction, which is the value is 1940 in hexadecimal, is loaded into the instruction register. So as you can see, the 1940 is loaded in the instruction register. And the PC is incremented. So from 300, it is incremented, it became 301. And then next, note that this process involves the use of a memory address registers and a memory buffer register. For simplicity, these intermediate registers are ignored. So next, the first 4 bits or the first hexadecimal digit in the IR indicate that the AC is to be loaded. The remaining 12 bits or the 3 hexadecimal digits specify the address or the 940 from which data are to be loaded. And then next, the next instruction, the 5941, as we can already see, the 5941 is fetched from location 301 because it's already in the program counter. And of course, and the PC is also incremented from 301 to 302. And then the old contents of the AC and the contents of location 941 are added, and the result is stored in the AC. So as we can see, it is already stored in the AC. And then the next instruction, 2941, is fetched from location 302. And then the PC is also incremented. From 302, it became 303. And then the contents of the AC are stored in location 941. So in this example, three instruction cycles, each consisting of a fetch cycle and an execute cycle, are needed to add the contents of location 940 to the contents of 941. With a more complex set of instructions, fewer cycles would be needed. Some older processors, for example, included instructions that contain more than one memory address. Thus, the execution cycle for a particular instruction on such processors could involve more than one reference to memory. Also, instead of memory references, an instruction may specify an I/O operation. So next figure is we have figure 3.6. So instruction cycle state diagram. So the execution cycle for a particular instruction may involve more than one reference to memory. Also, instead of memory references, an instruction may specify an I/O operation. With these additional considerations in mind, so this figure provides a more detailed look at the basic instruction cycle of figure 3.3. So this figure in the form of a state diagram. For any given instruction cycle, some states may be null and others may be visited more than once. The states can be described as follows. So first is we have the instruction address calculation or the IAC. So this is the IAC, instruction address calculation. It determines the address of the next instructions to be executed. Usually, this involves adding a fixed number to the address of the previous instruction. For example, if each instruction is 16 bits long and the memory is organized into 16-bit words, then add 1 to the previous address. If instead, the memory is organized as individually addressable 8-bit bytes, then add 2 to the previous address. Next is we have the instruction fetch or the IF. Read instructions from its memory location into the processor. Then next is we have the instruction operation decoding or the IOD. Analyze instruction, determine type of operation to be performed and operands to be used. And then next is we have the operand address calculation or the OAC. The operand address calculation. If the operation involves reference to an operand in memory or available via the I/O, then determine the address of the operand. And then next is we have the operand fetch. Operand fetch or the OF. Fetch the operand from memory or read it from the I/O. Then next is we have data operation or DO. Perform the data operation indicated in the instruction. Next is we have the operand store or the OS. So we have write the result into the memory or out to I/O. So states in the upper part of this figure involve an exchange between the processor and either memory or an I/O module. So states in the lower part of the diagram involve only internal processor operations. So we have this one. So this is the upper part, the instruction fetch, and operand store. So there is an involvement in exchange between the processor and either memory or I/O, while the lower part involve only internal processor operation, the instruction address calculation, the instruction operation coding, the operand address calculation, data operation, and operand address calculation. So, the OAC or the operand address calculation state appear twice, as we can see. We can see here two operand address calculation because an instruction may involve a read, write, or both. However, the action performed during that state is fundamentally the same in both cases, and so only a single state identifier is needed. Also note that the diagram allows for multiple operands, as you can see here, and multiple results, as we can see here in this diagram. Because some instructions on some machines require this. For example, the PDP-11 instructions add AB results in the following sequence of states. So we have IAC, next is IF, and then we have the IOD, and then we have the OAC, and then we have the OF, and then again we have the um, OAC again, and then the OF, and then we have the DO, and then the OAC, and then last is the OS. This is an example of there can be multiple operands or multiple results in the instruction cycle. And then finally, on some machines, a single instruction can specify an operation to be performed on a vector or one-dimensional array of numbers or a string or one-dimensional array of characters. As this figure indicates, this would involve repetitive operand fetch and or store operations. So next is we have table 3.1 that shows the classes of interrupts. So we have for program, timer, I/O, and hardware failure. So virtually, all computers provide a mechanism by which other modules such as I/O memory may interrupt the normal processing of the processor. So in this table list the most common classes of interrupts. The specific nature of these interrupts is examined in chapter 7 and 14. However, we need to introduce the concept now to understand more clearly the nature of the instruction cycle and the implications of interrupts on the interconnection structure. So we have a figure to illustrate using with interrupts or without interrupts. So next is we have figure 3.7, program flow of control without and with interrupts. So 3.7a, we have no interrupts. We have 3.7b, we have interrupts but short I/O wait. And letter C is we also employed interrupts but it has a long I/O or input-output wait. So interrupts are provided primarily as a way to improve processing efficiency. For example, most external devices are much lower than the processor. Suppose that the processor is transferring data to a printer using the instruction cycle scheme. And then after each write operation, the processor must pause and remain idle until the printer catches up. So in real life situation, of course, for example, in walking, we can have a comparison. Of course, if you are faster, for example, if you have a friend and then you walk faster, and because your friend is slower, for him to catch up or her to catch up, of course, you need to wait for it, just like here. And then the length of this pause may be on the order of many hundreds or even thousands of instruction cycles that do not involve memory. So what is the problem with the processor if it will pause and remain idle? Of course, we cannot maximize the processor because it has always have to wait to a slower device such as the printer. And then clearly, this is a very wasteful use of the processor. So for 3.7a, this illustrates the state of affairs. The user program performs a series of write calls interleaved with processing. So code segments, we have 1, 2, 3, refer to the sequences of instructions that do not involve the input-output. So the write calls are to an I/O program that is a system utility and that will perform the actual I/O operation. The I/O program consists of three sections. We have first is a sequence of instruction labeled 4, so this is 4 in the figure to prepare for the actual I/O operation. This may include copying the data to be output into a special buffer and preparing the parameters for a device command. And then next is the actual I/O command. Without the use of interrupts, this command is issued. The program must wait for the I/O device to perform the requested function or periodically poll the device. The program might wait by simply repeatedly performing a test operation to determine if the I/O operation is done. So next is a sequence of instructions labeled in 5 in the figure to complete the operation. This may include setting a flag indicating the success or failure of the operation. So because the I/O operation may take a relatively long time to complete, the I/O program is hung up waiting for the operation to complete. Hence, the user program is stopped at the point of the write call for some considerable period of time. So that's the problem with 3.7a. In this write, so the user program is halted. It will not go to segment 2 or 3 because it will wait for the IO program and IO command to finish before it returns again to the user's program control, and then it will proceed to segment 2, and then again there is a write program, so you need to have again a contact with with the IO device, and then we have the IO program and then the IO command. After that it has completed, it will proceed to segment 3, and then it will go on if the operation is like this. So without interrupts, um, the problem is that we will have a problem because of course, the processor, the time of the processor is very valuable. It should have already executed many instructions, but because of waiting for the IO device, it wastes its resources. So we have this one. And then we have 3.7b. We have interrupts. So for the next is we have is okay, because the IO operation may take a relatively long time to complete, as I've said. So it will just wait for the IO program to finish. So with interrupts, the processor can be engaged in executing other instructions while an IO operation is in progress. So consider the flow of control in figure 3.7b. So this one, interrupts with short IO wait. And then as before, the user program reaches a point at which it makes a system call in the form of a write call. The IO program that is invoked in this case consists only of the preparation code and the actual IO command. After few of these instructions have been executed, control returns to the user program. Meanwhile, the external device is busy accepting data from computer memory and printing it. This IO operation is conducted concurrently with the execution of instructions in the user program. So next is when the external device becomes ready to be serviced, that is when it is ready to accept more data from the processor, the I/O module for that external device sends an interrupt request signal to the processor. The processor responds by suspending operation of the current program, branching off to a program to service that particular I/O device known as the interrupt handler, and resuming the original execution after the device is serviced. The points at which interrupts occur are indicated by an asterisk in 3.7b. So for example, so we have another, just the same user program, and then we have the write call that needs for the IO device. So we have this, the IO and the IO command. So while the IO command is already processing the data, it will continue to to execute the user program. And if the IO command is already finished, there will be an interrupt handler um, taking the attention of the processor that the IO program has already, or the IO command has already finished its operation. And then so that's why there is here an asterisk for it, or an X mark, meaning you have to address it first. Then it will continue again its operation, and then we have, of course, the write call again, and then the IO program and IO command will execute, and then it will not wait for it to finish, but it will return to the control of the user program, executing its instructions. And then again, if the IO command is already finished, the interrupt handler will notify the processor uh, to service that IO finished IO command. And again, it will return to its uh, control to the user program. And it will happen as long as there is an IO, a write call for a specific IO device. So let us try to clarify what is happening in this figure. We have a user program that contains two write commands. So these are the two write commands. There is a segment of code at the beginning, then one write command, then a second segment of code, then a second write command, and then a third and final segment of code. The write command invokes the IO program provided by the OS. Similarly, The I/O program consists of a segment of code followed by an I/O command followed by another segment of code. The I/O command invokes a hardware I/O operation. So the difference between B and C, it's just that C, we have long I/O wait. But then again, they also have the same um, operation. And then there is no separate segment for 2A, 2B, 3A, and then 3B. Okay, next is we have, and then also, as you can see, for the first write is we have the IO program and IO command, and then it will finish its execution for segment 2 of the user program, and then the interrupt handler will notify again the processor that the IO has already finished its operation. So it really is synchronized with the right call of the user program to use the IO device. And then we have this so on and so forth depending on the user program. Okay, next is we have the figure 3.8, the transfer of control via interrupts. So from the point of view of the user program, an interrupt is just that, an interruption of the normal sequence of execution. So that is why it is called an interrupt, an interruption. So when the interrupt processing is completed, execution resumes as you can see in the figure. Thus, the user program does not have to contain any special code to accommodate interrupts. The processor and the operating system are responsible for suspending the user program and then resuming it at the same point. So that's why actually interrupts are also discussed in the discussion of the operating systems. So to further illustrate, or to explain, we have the user program and the interrupt handler. So the user program is executing its instruction as usual, and then there is an interrupt here, and then we need to add to service this another set of software of program that needs to be serviced first. So we have this interrupt handler, and then after um, finishing its execution, then we're going to return where the user program stops, and then will continue its um, execution of instruction. So just like in a real world situation, for example, if you're doing something, for example, you're making your document, and then for example, your parents interrupted you or talked to you, and then after talking to you, because it's very urgent, so you need to talk to it, so you have to remember where did you stop, and after that conversation, you need to return doing their document. Of course, you have to remember where did you stop and continue doing your document. So that is an example in a real world situation of interrupts. Okay, next is we have another figure, 3.9, instruction cycle with interrupts. So to accommodate interrupts, an interrupt cycle is added to the instruction cycle as in this figure. So this is the one, check for interrupts. And then if there is an interrupt, you have to process the interrupt. So in the interrupt cycle, the processor checks to see if any interrupts have occurred, indicated by the presence of an interrupt signal. If no interrupts are pending, the processor proceeds to the fetch cycle and fetches the next instruction of the current program. If an interrupt is pending, the processor does the following. First, it suspends the execution of the current program being executed and saves its context. This means saving the address of the next instruction to be executed, current contents of the program counter, and any other data relevant to the processor's current activity. It sets the program counter to the starting address of an interrupt handler routine. And then the processor proceeds to the fetch cycle and fetches the first instruction in the interrupt handler program, which will service the interrupt. The interrupt handler program is generally part of the operating system. Typically, this program determines the nature of the interrupt and performs whatever actions are needed. In the example, we have been using the handler determines which I/O module generated the interrupt and may branch to a program that will write more data out to that I/O module. When the interrupt handler routine is completed, the processor can resume execution of the user program at the point of interruption. It is clear that there are some overhead involved in this process, Extra instructions must be executed in the interrupt handler to determine the nature of the interrupt and to decide on the appropriate action. Nevertheless, because of the relatively large amount of time that would be wasted by simply waiting on an I/O operation, the processor can be employed with much more efficiently with the use of interrupts. Okay, so we have this one for additional explanation. So we have the instruction cycle. So this is the original instruction cycle. And then we added for checking of interrupts, we have the interrupt cycle. So if there is no interrupt here, it will continue its execution, fetching the next instruction and of course execute the instruction. If there is a pending interrupt here, it needs to of course service that interrupt, and then after, so that's why it's pointing in here, after it services all the programs that need to be serviced, it will continue to fetch the next instruction of the user program. So that is the instruction cycle with interrupts. Okay, next is we have figure 3.10, program timing, or the short I/O wait. So to appreciate the gain and efficiency because of interrupts, consider figure 3.10, which is a timing diagram based on the flow control in figures 3.7a and 3.7b. So 3.7a and 7b, as you can remember, there are employing interrupts. 3.7, we have this for long I/O wait and short I/O wait. So in this figure, user program code segments are shaded green. So we have the shaded green, and then the I/O program code segments are shaded gray. So for segment 4 and 5, as you can remember. So figure 3.10a shows the case in which interrupts are not used. So for this one, there is no interrupts as in figure 3.7a. And then the processor must wait while an I/O operation is performed. So this black box here or area, is it this where the processor waits. Also, as I've already mentioned, it is a waste for time for the processor because this time frame it should have executed more instructions, but because it has to wait for the I/O to finish the I/O operation, the processor needs to be idle. So next is we have figures 3.7b and 3.10b. So we have interrupts specifically for short I/O wait. Assume that the time required for the I/O operation is relatively short, less than the time to complete the execution of instructions between write operations in the user program. In this case, the segment of code labeled code segment 2 is interrupted. So for this one, so that's why there is a 2A and 2B because 2 is in the segment 2 is interrupted of segment 5. A portion of the code, which is 2A, executes while the I/O operations is performed, and then the interrupt occurs upon the completion of the I/O operations. After the interrupt is serviced, execution resumes with the remainder code segment of 2, which is 2B. This also happens with 3A and 3B. Okay, next is we have 3.11. This pertains for 3.7c. So program timing of long I/O wait. So it also compares the without interrupts and with interrupts. So the more typical case, especially for a slow device such as a printer, is that the I/O operation will take much more time than executing a sequence of user instruction. So for 3.7c, which is the long I/O wait, indicates the state of affairs. In this case, the user program reaches the second write call before the I/O operation spawned by the first call is complete. So that's why, as you can see with figure 3.7c, the interrupt handle only finished on the next write call. And then the result is that the user program is hung up at that point. When the preceding I/O operation is complete, this new write call may be processed and a new I/O operation may be started. So in this figure, shows the timing for this situation with and without the use of interrupt. So this 3.11a as the same with with the previous figure. Okay, so in this figure we have the use of without the use of interrupts and with the use of interrupts. So we can see that there is still a gain in efficiency because part of the time during which the I/O operation is underway overlaps with the execution of user instruction. So this one. So I/O operation concurrent with processor executing. Then also the problem is with long I/O wait the processor needs also to wait or to be idle. So ideally, so it's better for have the short I/O wait with interrupts. This only happens, additionally, this only happens when the I/O operation is too long to finish. Okay, next is we have figure 3.12. So another is we have instruction cycle state diagram. Just the same with the previous figure with the instruction cycle diagram. It's just that it also included the interrupts. So figure 3.12 shows a revised instruction cycle state diagram that includes interrupt cycle processing. And then for the next figure 3.13, we have the transfer of control with multiple interrupts. So two approaches can be taken to dealing with multiple interrupts. What if there are many programs that need to be serviced? The first is to disable interrupts while an interrupt is being processed, of course. And a disabled interrupt simply means that the processor can and will ignore the interrupt request signal. If an interrupt occurs during this time, it generally remains pending and will be checked by the processor after the processor has enabled interrupts. Thus, when a user program is executing and an interrupt occurs, interrupts are disabled immediately. After the interrupt handler routine completes, interrupts are enabled again before resuming the user program, and the processor checks to see if additional interrupts have occurred. So this approach is nice and simple as interrupts are handled in strict sequential order as in figure 3.13a. For example, for the user program, from here there is an interrupt. So we have an interrupt handler X. After servicing this interrupt and it's finished its execution, it will return to the user program, and then another interrupt is being done by interrupt handler Y. So processor needs to service first. Then after its execution, it will return to the user program. Since interrupt handler X first notify the processor as an interrupt, it will be handled first. And next is we have this interrupt handler Y. So what is the drawback of 3.13a? So it does not take into account relative priority or time critical needs. It only focuses which is the first interrupt it will service, and then it will after servicing the first interrupt based on the timeline, and then the next interrupt will be serviced, disregarding if it's time critical or it is a priority. So for example, when an input arrives from the communications line, it may need to be absorbed rapidly to make room for more input. If the first batch of input has not been processed before the second batch arrives, data may be lost. So that's why this is an example of a time critical interrupt. So a second approach, which is 3.13b, so the nested interrupt processing, is to define priorities for interrupts and to allow an interrupt of higher priority to cause a lower priority interrupt handler to be itself interrupted. So, for example, we have the user program, and then from this one, there is an interrupt handler that wants the service of the processor. So the processor will service this interrupt handler X, and then another interrupt occur. Since interrupt handler Y is time critical or has more priority than interrupt handler X, this interrupt will also be interrupted. It will stop its execution, and then the processor will service first the interrupt handler Y, and then after finishing the execution, it will return to the interrupt handler X to finish its execution here, and then after finishing the interrupt handler's service request, it will return to the user program. So that is the nested interrupt processing. Okay, next is we have figure 3.14. So we have an example time sequence of multiple interrupts. As an example of the second approach, so consider a system with three I/O devices. We have a printer and then a disk. This we have the disk and a communications line with increasing priorities of 2, 4, and 5 respectively. And then figure 3. This figure illustrates a possible sequence. So at user program begins at T0 or at time is equal to 0. And then at time equal to 10, a printer interrupt occurs. So that's why there is a printer interrupt here. And then user information is placed on the system stack and executes, and the execution continues at the printer interrupt service routine or the ISR. So while this routine is still executing, so at time 15, so the printer is already serviced by the processor. So at time 15, a communications interrupt occurs. Since you can see it has higher priority, so that's why the interrupt is honored. So the printer ISR is interrupted here, and then its state is pushed back into the stack to remember the last state of the printer ISR, and the execution continues at the communications ISR. So or the internet interrupt service routine. Then while this routine is executing, a disk interrupt occurs at t is equal to 0. So we have t is equal to 0. Because this interrupt is of lower priority, as you can see, uh, this is already T15, but it finishes T25, and then it also says that the disk interrupt occurs at T20. Since disk has a lower priority, so what happens? Disk ISR is being, it's not neglected, it's just that it becomes pending because the communication ISR has a higher priority. So it is simply held and the communications ISR runs to completion. That's why it is completed at T is equal to 25. So when the ISR is completed at T25, so it will return to the printer service routine. So the previous processor state is restored, which is the execution of the printer ISR. So it will continue to execute inside the printer service request. However, before even a single instruction in that routine can be executed, because there is a pending disk interrupt service routine, so the processor honors the higher priority, which is the disk. So disk has higher priority than the printer, and it controls transfer to the disk ISR. So that's why it goes at T25, it goes to the disk. And of course, printer has a lower priority. It has finished its execution at T35. Okay. So, okay, after T35, the printer ISR resumes. So that's why this is here. When that routine completes at T40, so the printer ISR completes at T40, the control finally returns to the user program at last. And the user program will continue its execution unless there is another interrupt that will be coming depending on the priority and its time critical. It is very critical. So that's how 3.14 is done with multiple interrupts. Okay, next is we have the I/O function. So an I/O module such as a disk controller can exchange data directly with the processor. Just as the processor can initiate a read or write with memory, designating the address of a specific location, the processor can also read data from or write data to an I/O module. In this later case, the processor identifies a specific device that is controlled by a particular I/O module. Thus, an instruction sequence similar in form to that of figure 3.5 could occur with I/O instructions rather than memory referencing instructions. In some cases, it is desirable to allow I/O exchanges to occur directly with memory. In such a case, the processor grants to an I/O module the authority to read from or write to memory so that the I/O memory transfer can occur without tying up the processor. During such a transfer, the I/O module issues read or write commands to memory, relieving the processor of responsibility for the exchange. So this operation is known as direct memory access, and it is also discussed in chapter 7. So next is we have the figure 3.15, all about computer modules, which is composed of memory, I/O module, and the CPU. So a computer consists of a set of components or modules of three basic types. As I've mentioned, we have processor, memory, and I/O that communicate with each other. In effect, a computer is a network of basic modules. Thus, there must be paths for connecting the modules. So the collection of paths connecting the various modules is called the interconnection structure. The design of this structure will depend on the exchanges that must be made among modules. So for this figure, suggest the types of exchanges that are needed by indicating the major forms of input and output for each module type. For memory, typically, a memory module will consist of n words of equal length. So each word is assigned a unique numerical address from 0, 1 to n minus 1. A word of data can be read or written into the memory. The nature of the operation is indicated by the read and write control signals. The location for the operation is specified by an address. So next is we have an I/O module. From an internal or to the computer system point of view, I/O is functionally similar to memory. There are two operations. So that's why they are similar because they also have read and write for I/O module. It also has a read and write for memory. So further, an I/O module may control more than one external device. We can refer to each of the interfaces to an external device as a port and give each a unique address such as 0, 1, or to m-1. In addition, there are external data paths for the input and output of data with an external device. Finally, an I/O module may be able to send interrupt signals to the processor, such as if you're familiar with computer, what are the input and output devices? This input and output devices, this connects actually to the I/O module by means of ports, our keyboards, our monitors, our mouse. So that's already an example of an I/O devices that is connected to the I/O module again by means of ports. And then but not the least is we have the processor. So the processor reads in instructions and data, writes out data after processing, and uses control signals to control the overall operation of the system. It also receives interrupt signals. So next is we have the interconnection structure must support the following types of transfers. So the list here, preceding list defines the data to be exchanged. The interconnection structure must support these following types of transfer. First is we have memory to processor. So the processor reads an instruction or a unit of data from memory. Next is we have processor to memory. The processor writes a unit of data to memory. And then we have I/O to processor. The processor reads data from I/O device via an I/O module. Then we have processor to I/O. The processor sends data to the I/O device and then I/O to or from memory. For these two cases, an I/O module is allowed to exchange data directly with memory without going through the processor using direct memory access. So as not to disturb the processor of its execution. So it has a direct memory access. Over the years, a number of interconnection structures have been tried. By far, the most common are the bus and various multiple bus structures, and second, point-to-point interconnection structures with packetized data transfer. So we devote the remainder of this chapter for a discussion of these structures. So next is we have bus interconnection. So the bus was the dominant means of computer system component interconnection for decades. For general purpose computers, it has gradually given way to various point-to-point interconnection structures which now dominate computer system design. However, bus structure are still commonly used for embedded systems, particularly microcontrollers. So in this section, we give a brief overview of the bus structure. So as a definition, A bus is a communication pathway connecting two or more devices. A key characteristic of a bus is that it is a shared transmission medium. Multiple devices connect to the bus, and a signal transmitted by any one device is available for reception by all other devices attached to the bus. If two devices transmit during the same time period, their signals will overlap and become garbled. Thus, only one device at a time can successfully transmit. So that is the function of the bus. The first one who transmit the signal that it will send through the bus, it will be the first to use the bus. And then typically, a bus consists of multiple communication pathways or lines. Each line is capable of transmitting signals representing binary 1 and binary 0. Over time, a sequence of binary digits can be transmitted across a single line. Taken together, several lines of a bus can be used to transmit binary digits simultaneously or in parallel. For example, an 8-bit unit of data can be transmitted over 8 bus lines. So it is in parallel. Computer systems contain a number of different buses that provide pathways between components at various levels of the computer system hierarchy. A bus that connects major computer components such as processor, memory, or and the I/O is called a system bus. The most common computer interconnection structure are based on the use of one or more system buses. So aside from system bus, we have another bus which is the data bus. So a system bus consists typically of from about 50 to 100 of separate lines. So the data lines provide a path for moving data among system modules. These lines collectively are called the data bus. So, of course, data, this is only for transmitting data. So, the data bus may consist of 32, 64, 128, or even more separate lines, just a power of 2, the number of lines being referred to as the width of the data bus. Because each line can only carry one bit at a time, the number of lines determine how many bits can be transferred at a time. The width of the data bus is a key factor in determining overall system performance. For example, if the data bus is 32 bits wide and each instruction is 64 bits long, then the processor must access the memory module twice during each instruction cycle. Okay, another bus that we have to encounter here is we have the address and control bus. So next is the address lines are used to designate the source or destination of the data on the data bus. For example, if the processor wishes to read a word, which can be 8, 16, or 32 bits of data from memory, it puts the address of the desired word on the address lines. Clearly, the width of the address bus determines the maximum possible memory capacity of the system. Furthermore, the address lines are generally also used to address I/O ports. Typically, the higher order bits are used to select a particular module on the bus, and the lower order bits select a memory location or I/O port within the module. For example, on an 8-bit address bus, the address 01111111, which is 8 bits, and below might reference locations in a memory module or module 0 with 128 words of memory and address 1 and then 00000000 7 zeros and above refer to device attached to an I/O module, which is module 1. Then we have another, the control lines are used or the control bus are used to control the access to and the use of the data and address lines. Because the data and address lines are shared by all components, there must be a means of controlling their use. Control signals transmit both command and timing information among system modules. Timing signals indicate the validity of data and address information. Command signals specify operations to be performed. Typical control lines include: first is memory write, causes data on the bus to be written into the address location. Next is we have memory read, causes the data from the address location to be placed on the bus. And then we have I/O write, causes data on the bus to be output to the addressed I/O port. And then I/O read causes data from the addressed I/O port to be placed on the bus. And then we have transfer ACK or acknowledgement indicates that data have been accepted from or placed on the bus. Next is we have bus request indicates that a module needs to gain control of the bus. Bus grant indicates that a requesting module has been granted control of the bus. And then we also have interrupt request indicates that an interrupt is pending. And then interrupt ACK or interrupt acknowledgement acknowledges that the pending interrupt has been recognized. We also have the clock. It is used to synchronize operation and reset initializes all modules. Okay, next is further discussion of the bus is we have figure 3.16, the bus interconnection scheme. So each line is assigned a particular meaning or function. Although there are many different bus designs, on any bus, the lines can be classified into three functional groups such as data, address, and control lines. As we can see, we have the data, address, and control lines. Okay, in addition, there may be a power distribution lines that supply power to the attached modules. So the operation of the bus is as follows. If one module wishes to send data to another, it must do two things. First, obtain the use of the bus. Of course, you need to make sure that no other module is using the bus. And number two, transfer data via the bus. If one module wishes to request data from another module, it must first obtain the use of the bus also, and second, transfer a request to the other module over the appropriate control and address lines. It must then wait for that second module to send data. Okay, aside from bus, we have this another connection. We have the point-to-point interconnect. So the shared bus architecture was the standard approach to interconnection between the processor and other components such as memory, I/O, and others for decades. But contemporary systems increasingly rely on point-to-point interconnection rather than shared buses. So the principal reason driving the change from bus to point-to-point interconnect was the electrical constraints encountered with increasing the frequency of wide synchronous buses. At higher and higher data rates, it becomes increasingly difficult to perform the synchronization and arbitration functions in a timely fashion. Further, with the advent of multi-core chips, with multiple processors and significant memory on a single chip, it was found that the use of a conventional shared bus on the same chip magnified the difficulties of increasing bus data rate and reducing bus latency. To keep up interconnect has lower latency, higher data rate, and better scalability. So that's why point-to-point interconnect is also considered. So first is we have the QPI or the Quick Path Interconnect. So in this section, we look at an important and representative example of the point-to-point interconnect approach, the Intel's Quick Path Interconnect or the QPI, which was introduced in 2008. The following are significant characteristics of QPI and other point-to-point interconnect schemes. For this has multiple direct connections. Multiple components within the system enjoy direct pairwise connection to other components. This eliminates the need for arbitration found in shared transmission systems. Another is we have the layered protocol architecture. As found in network environments such as the TCP/IP-based data networks, the transmission control protocol or the internet protocol, this processor level interconnects use a layered protocol architecture rather than the simple use of control signals found in shared bus arrangement. And then we have another, the packetized data transfer. Data are not sent as a raw bit stream. Rather, data are sent as a sequence of packets, each of which includes control headers and error control codes. So we have an illustration in figure 3.17, multi-core configurations using QPI. So this figure illustrates a typical use of QPI on a multi-core computer. So we have four cores here. So the QPI links indicated by the green arrow pairwise, okay, form a switching fabric that enables data to move throughout the network. Direct QPI connections can be established between each pair of core processors. So, if core in this figure needs to access the memory controller in D, so core to D, so it sends requests through either cores B or C, which must in turn forward that request on the memory controller in core D. So similarly, larger systems with 8 or more processors can be built using processors with 3 links and routing traffic through intermediate processors. So in addition, QPI is used to connect an I/O module called an I/O hub, or IOH. So we have the I/O hub here. The IOH acts as a switch directing traffic to and from the I/O devices. Typically, in newer systems, the link from the IOH to the I/O device controller uses an interconnect technology called the PCI Express or the PCIe, which is described on the next on this chapter. So the IOH translates the QPI protocols and formats and the PCIe protocols and formats. A core also links to a main memory module. So we have this main memory module for the DRAM. And then typically the memory uses dynamic access memory as I've said, DRAM, using a dedicated memory bus. So another figure is as QPI said is using layered approach. So in this figure 3.18, these are the QPI layers. So QPI is defined as a four-layer protocol architecture encompassing the following layers. First is we have the physical, so consists of the actual wires carrying the signals, as well as circuitry and logic to support ancillary features required in the transmission and receipt of the ones and zeros. The unit transfer at the physical layer is 20 bits, which is called fit or physical units in fits. And then next, okay, let's return to the previous slide. Link. We have this link responsible for reliable transmission and flow control. The link's layer unit of transfer is 80-bit FLIT or flow control unit FLIT. And then next is we have the routing, provides the framework for directing packets through the fabric. And last but not the least is we have the protocol, the high-level set of rules for exchanging packets of data between devices. A packet is comprised of an integral number of flits. So next is another figure. We have 3.19, the physical interface of the Intel QPI interconnects. So this figure shows the physical architecture of a QPI port. The QPI port consists of 84 individual links grouped as follows. So each data path consists of a pair of wires that transmits data one bit at a time. The pair is referred to as a lane. So we have here transmission and reception lanes. There are 20 data lanes in each direction, transmit and receive, plus a clock lane in each direction. Thus, QPI is capable of transmitting 20 bits in parallel in each direction. The 20-bit unit is referred to as a FIT. Typical signaling speeds of the link in current products calls for operation at 6.4 giga transfers per second. At 20 bits per transfer, that adds up to 16 gigabytes per second. And since QPI links involve dedicated bidirectional pairs, the total capacity is 32 gigabytes per second, which is very large. The lanes in each direction are grouped into four quadrants of 5 lanes each. So 1, 2, 3, 4, 5. In some applications, the link can also operate at half or quarter widths in order to reduce power consumption or work around failures. So the form of transmission on each lane is known as differential signaling or balanced transmission. With balanced transmission, signals are transmitted as a current that travels down one conductor and returns to the other. The binary value depends on the voltage difference. Typically, one line has a positive voltage value and the other line has zero voltage, and one line is associated with binary 1 and one line is associated with binary 0. Specifically, The technique used by QPI is known as the low voltage differential signaling, or the LVDS. In a typical implementation, the transmitter injects a small current into one wire or the other, depending on the logic level to be sent. The current passes through the resistor at the receiving end and then returns in the opposite direction along the other wire. The receiver senses the polarity of the voltage across the resistor to determine the logic level. So next is we have figure 3.20, all about QPI multi-lane distribution. Another function performed by the physical layer is that it manages the translation between 80-bit flits and 20-bit fits using a technique known as multi-lane distribution. So the flits can be considered as a bit stream that is distributed across the data lanes in a round-robin fashion, first bit to first lane, second bit to second lane, and others, as illustrated in this figure. So this approach enables QPI to achieve very high data rates by implementing the physical link between two ports as multiple parallel channels. So next is we have another elaboration of the QPI link layer. So the QPI link layer performs two key functions: flow control and error control. So these functions are performed as part of the QPI link layer protocol and operate on the level of the flit, or the flow control unit. Each flit consists of a 72-bit message payload and an 8-bit error control code called a cyclic redundancy check, or CRC. So the error control codes is discussed separately in chapter 5. A fleet payload may consist of data or message information. The data fleets transfer the actual bits of data between cores or between a core and an IOH, or the IO hub. The message fleets are used for such functions as flow control, error control, and cache coherence. Cache coherence is also discussed in chapter 5 and 17. The flow control function is needed to ensure that a sending QPI entity does not overwhelm a receiving QPI entity by, say, sending data faster than the receiver can process the data, and clear buffers for more incoming data. To control the flow of the data, QPI makes use of a credit scheme. During initialization, a sender is given a set of number of credits to send flits to a receiver. Whenever a flit is set to the receiver, the sender decrements its credit counters by 1 credit. Whenever a buffer is freed at the receiver, a credit is returned to the sender for that buffer. Thus, the receiver controls that pace at which data is transmitted over a QPI link. Occasionally, a bit transmitted at the physical layer is changed during transmission due to noise or some other phenomenon. So this is inevitable. So the error control function at the link layer detects and recovers from such bit errors and isolate higher layers from experiencing bit errors. The procedure works as follows for a flow of data from system A to system B. Number one, as mentioned, each 80-bit flit includes an 8-bit CRC, or cyclic redundancy check field. The CRC is a function of the value of the remaining 72 bits. On transmission, A calculates CRC value for each flit and inserts that value into the flit. Number two, when a flit is received, B calculates a CRC value for the 72-bit payload and compares this value with the value of the incoming CRC value in the fleet that is computed by A. If the two CRC values do not match, so there is an error, and error has been detected. Number three, when B detects an error, it sends a request to A. It's either to retransmit the fleet that is in error. However, because A may have had sufficient credit to send a stream of fleets, so that additional fleets have been transmitted after the fleet in error and before A receives the request to retransmit. Therefore, the request is for A to back up and retransmit the damaged fleet plus all the subsequent fleets. So A must have a backup after it has sent the data plus the CRC. Okay, next is we have the QPI routing and protocol layers. So the routing layer is used to determine the course that a packet will traverse across the available system interconnects. Routing tables are defined by firmware and describe the possible paths that a packet can follow. In small configurations, such as a two-pack socket platform, the routing options are limited and the routing tables quite simple. For larger systems, the routing table options are more complex given the flexibility of routing and rerouting traffic depending on number one, devices are populated in the platform, number two, system resources are partitioned, and number three, reliability events result in mapping around a failing resource. So for the QPI protocol layer, in this layer, the packet is defined as the unit of transfer. The packet contents definition is standardized with some flexibility allowed to meet differing market segment requirements. One key function performed at this level is a cache coherency protocol, which deals with making sure that main memory values held in multiple caches are consistent. A typical data packet payload is a block of data being sent to or from a cache. Okay, so much with QPI. Next is we have the Peripheral Component Interconnect or the PCI. So the PCI is a popular high bandwidth processor independent bus that can function as a mezzanine or peripheral bus. Compared with other common bus specifications, PCI delivers better system performance for high-speed I/O subsystems such as graphic display adapters, network interface controllers, and disk controllers. So that's why PCI's application in the computer system are mostly for graphic display adapters or the graphics card of the computer system or network interface controllers and of course disk controllers. So Intel began work on PCI in 1990 for its Pentium-based systems. Intel soon released all the patents to the public domain and promoted the creation of an industry association, the PCI Special Interest Group or SIG, to develop further and maintain the compatibility of the PCI specifications. The result is that PCI has been widely adopted and is finding increasing use in personal computer, workstation, and server systems. Because the specification is in the public domain and is supported by a broad cross-section of the microprocessor and peripheral industry, PCI products built by different vendors are compatible. Actually, that's a good move of Intel. As with the system bus discussed in the preceding sections, the bus-based PCI scheme has not been able to keep pace within the data rate demands of attached devices. Accordingly, because of this, a new version known as the PCI Express or the PCIe has been developed. PCIe, as with QPI, is a point-to-point interconnect scheme intended to replace bus-based schemes such as the older PCI. A key requirement for PCIe is high capacity to support the needs of higher data rate I/O devices such as gigabit and I/O devices such as gigabit internet. Another requirement deals with the need to support time-dependent data streams. Applications such as video on demand and audio redistributions are putting real-time constraints on servers too. Many communications applications and embedded PC control systems also process data in real time. So today's platforms must also deal with multiple concurrent transfers at ever-increasing data rates. It is no longer acceptable to treat all data as equal. It is more important, for example, to process streaming data first since late real-time data is as useless as no data. Data needs to be tagged so that an I/O system can prioritize its flow throughout the platform. So next slide is we have the typical configuration using the PCIe or the PCI Express. So this figure shows a typical configuration that supports the use of PCIe. We have a root complex device, also referred to as chipset or a host bridge, connects the processor and the memory subsystem to the PCI Express switch fabric comprising one or more PCIe and PCIe switch devices. The root complex acts as a buffering device to deal with difference in data rates between I/O controllers and memory and processor components. The root complex also translates between PCIe transaction formats and the processor and memory signal and control requirements. The chipset will typically support multiple PCIe ports, some of which attach directly to the PCIe device, and one or more that attach to a switch that manages multiple PCIe streams. PCIe links from the chipset may attach to the following kinds of devices that implement PCIe. It can be either a switch, the switch manages multiple PCIe streams. And then we have the PCIe endpoint, so an I/O device or controller that implements PCIe, such as a gigabit Ethernet switch, a graphics or video controller, disk interface, or a communications controller. So for this example, we have three PCIe endpoints. Then we have legacy endpoint. Legacy endpoint category is intended for existing designs that have been migrated to PCI Express, and it allows legacy behavior such as use of I/O space and lock transactions. PCI Express endpoints are not permitted to require the use of I/O space at runtime and must not use lock transactions. By distinguishing these categories, it is possible for a system designer to restrict or eliminate legacy behaviors that have negative impacts on system performance and robustness. Legacy endpoint meaning it services older devices or using instruction sets or operations that are similar to the older PCI. Then we have the PCIe or the PCI bridge, allows older PCI devices to be connected to PCIe based systems. Okay, next is we have another figure. We have figure 3.22, the PCIe protocol layers. The same with QPI, it also has these layers. As with QPI, PCIe interactions are defined using a protocol architecture. The PCIe protocol architecture encompasses the following layers as in this figure. We have the physical data link and transaction. So physical consists of the actual wires carrying the signals, as well as circuitry and logic to support ancillary features required in the transmission and receipt of the zeros and ones. Next is we have data link. It's responsible for reliable transmission and flow control. Data packets are generated and consumed by the DLL or the data link layer. And then this consumed by the DLL are called data link layer packets or the DLLPs. Then next is we have transaction. Generates and consumes data packets used to implement load or store data transfer mechanisms and also manages the flow control of those packets between the two components on a link. Data packets generated and consumed by the TL are called transaction layer packets. So TL is transaction layer. Above the TL are software layers that generate read and write requests that are transported by the transaction layer to the I/O devices using a packet-based transaction protocol. And then the next figure, 3.23, is the illustration of the PCIe multi-lane distribution, similar with QPI. As I've said, it is similar to QPI. PCIe is a point-to-point architecture. Each PCIe port consists of a number of bidirectional lanes. So note that in QPI, the lane refers to transfer in one direction only. Transfer in each direction in a lane is by means of differential signaling over a pair of wires. A PCI port can provide 1, 4, 6, 16, or 32 lanes. In what follows, we refer to the PCIe 3.0 specification as introduced in late 2010. As with QPI, PCIe uses a multi-lane distribution technique. So in this figure, shows an example for a PCIe port consisting of 4 lanes. So 1, 2, 3, 4. Data are distributed to the 4 lanes 1 byte at a time using a simple round-robin scheme. At each physical lane, data are buffered and processed 16 bytes, 128 bits at a time. Each block of 128 bits is encoded into a unique 130-bit code word for transmission. This is referred to as 128 byte over 130 bits encoding, or correct me, 128 bits over 130 bits encoding. Thus, the effective data rate of an individual lane is reduced by a factor of 128 over 130. To understand the rationale for the 128-bit over 130-bit encoding, note that unlike QPI, PCIe does not use its clock line to synchronize the bit stream. That is, the clock line is not used to determine the start and end point of each incoming bit. It is used for other signaling purposes only. However, it is necessary for the receiver to be synchronized with the transmitter so that the receiver knows when each bit begins and ends. If there is any drift between the clocks used for bit transmission and reception of the transmitter and receiver, errors may occur. To compensate for the possibility of drift, PCIe relies on the receiving synchronizing with the transmitter based on the transmitted signal. As with QPI, PCIe uses differential signaling over a pair of wires. Synchronization can be achieved by the receiver looking for transitions in the data and synchronizing its clock to the transition. However, consider that with a long string of ones or zeros using differential signaling, the output is a constant voltage over a long period of time. Under these circumstances, any drift between the clocks of transmitter and receiver will result in loss of synchronization between the two. So next is we have another figure, figure 3.24, PCIe transmit and receive block diagrams. So we have 3.24a is for the transmitter and we have 3.24b for the receiver. A common approach and the one used in PCIe 3.0 to overcoming that problem as discussed in the previous slide of a long string of bits of one value is scrambling. Scrambling, which does not increase the number of bits to be transmitted, is a mapping technique that tends to make the data appear more random. So the scrambling tends to spread out the number of transitions so that they appear at the receiver more uniformly spaced, which is good for synchronization. Also, other transmission properties such as spectral properties are enhanced if the data are more nearly of a random nature rather than constant or repetitive. So another technique that can aid in synchronization aside from scrambling is encoding rather, in which additional bits are inserted into the bit stream to force transitions. For PCIe 3.0, each group of 128 bits of input is mapped into 130-bit block by adding a 2-bit block sync header. The value of the header is 10 for a data block and 01 for what is called an ordered set block, which refers to a linked level information block. So this figure illustrates the use of scrambling and encoding. So the scrambled output is then fed into the 128-bit over 130-bit encoder, which buffers 128 bits and then maps the 128-bit block into a 130-bit block. So this block then passes through a parallel to serial converter and transmitted one bit at a time using differential signaling. After the receiver, a clock is synchronized to the incoming data to recover the bit stream. This then passes through a serial to parallel converter to produce a stream of 130-bit blocks. Each block is passed through a 128-bit over 130-bit decoder to recover the original scrambled bit pattern, which is then descrambled to produce the original bit stream. Using these techniques rather, a data rate of 16 gigabytes per second can be achieved. One final detail to mention. Each transmission of a block of data over a PCI link begins and ends with an 8-bit framing sequence intended to give the receiver time to synchronize with the incoming physical layer bit stream. Okay, next is we have the PCIe transaction layer or the TL. So the transaction layer receives read and write requests from the software above the TL and creates request packets for transmission to a destination via the link layer. Most transactions use a split transaction technique, which works in the following fashion. A request packet is sent out by a source PCIe device, which then waits for a response called a completion packet. The completion following a request is initiated by the computer only when it has the data and or the status ready for delivery. Each packet has a unique identifier that enables completion packets to be directed to the correct originator. With a split transaction technique, the completion is separated in time from the request, in contrast to a typical bus operation in which both sides of a transaction must be available to seize and use the bus. Between the request and the completion, other PCIe traffic may use the link. TL messages and some write transactions are posted transactions, meaning that no response is expected. The TL packet format supports 32-bit memory addressing and extended 64-bit memory addressing. Packets also have attributes such as no snoop, relaxed ordering, and priority, which may be used to optimally route these packets through the I/O subsystem. So next is the TL supports four address spaces, such as first is we have memory. The memory space includes system main memory. It also includes PCIe I/O devices. Certain ranges of memory addresses map into I/O devices. Next is we have the I/O. So this address space is used for legacy PCI devices with reserved memory address ranges used to address legacy I/O devices. Next is we have configuration. This address space enables the TL to read-write configuration registers associated with I/O devices. And last is we have the message. This address space is for control signals related to interrupts, error handling, and power management. Next is we have the table 3.2, the PCIe TLP transaction types. So this table shows the transaction types provided by the TL. For memory, I/O, and configuration address spaces, there are read and write transactions. In the case of memory transactions, there's also a read lock request function. Locked operations occur as a result of device drivers requesting atomic access to registers on a PCIe device. A device driver, for example, can automatically read, modify, and then write to a device register. To accomplish this, the device driver causes the processor to execute an instruction or set of instructions. The root complex converts this processor instruction into a sequence of PCIe transactions which perform individual read and write requests for the device driver. If these transactions must be executed atomically, the root complex locks the PCIe link while executing the instructions. This locking prevents transactions that are not part of the sequence from occurring. This sequence of transaction is called a locked operation. The particular set of processor instructions that can cause a locked operations to occur depends on the system chipset and processor architecture. To maintain compatibility with PCI, PCIe supports both Type 0 and Type 1 configuration cycle. A Type 1 cycle propagates downstream until it reaches the bridge interface hosting the bus or the link that the target device resides on. The configuration transaction is converted on the destination link from Type 1 to Type 0 by the bridge. Finally, completion messages are used with split transactions for memory, I/O, and configuration transactions. Then next is we have the figure. We have 3.25 PCIe control protocol data unit format. So PCIe transactions are conveyed using transaction layer packets, which are illustrated in this figure. We have 3.25A. So a TLP originates in the transaction layer of the sending device and terminates at the transaction layer of the receiving device. Upper layer software sends to the transaction layer the information needed to the TL to create the core of TLP. So which consists of the following fields. First is we have header. The header describes the type of packet and includes information needed by the receiver to process the packet, including any needed routing information. The internal header format is discussed subsequently. Then next is we have the data. A data field of up to 4096 bytes, so this is the data, may be included in the TLP. Some TLPs do not contain a data field. We have the ECRC, the optional end-to-end CRC, or the cyclic redundancy check field, enables the destination, the TL layer, to check for errors in the header and data portions of the TLP. So the purpose of the PCIe data link layer is to ensure reliable delivery of packets across the PCIe link. The DLL participates in the formation of DLPs and also transmits DLLPs. Data link layer packets originate at the data link layer of a transmitting device and terminate at the DLL of the device on the other end of the link. So it also shows the format of the DLLP. So this is the format of the DLLP. There are three important groups of DLLP used in managing a link. So we have the flow control packets, power management packets, and the TLP acknowledgement and NAK packets, or the negative acknowledgement packets. Power management packets are used in managing power platform budgeting. Flow control packets regulate the rate at which TLPs and DLLPs can be transmitted across a link. The acknowledgement and the negative acknowledgement packets are used in TLP processing as discussed. So the DLL adds two fields to the core of the TLP created by the TL, a 16-bit sequence number and a 32-bit layer CRC, or the LCRC. Whereas the core fields created at the TL are only used at the destination TL. The two fields are added by the DLL are processed at each intermediate node on the way from source to destination. When a TLP arrives at a device, the DLL strips off the sequence number and LCRC fields and checks the LCRC. There are two possibilities. If no errors are detected, the core portion of the TLP is handed up to the local transaction layer. If this receiving device is the intended destination, then the TL processes the TLP. Otherwise, the TL determines a route for the TLP and passes it back down to the DLL for transmission over the next link on the way to the destination. Number two, if an error is detected, the DLL schedules a negative acknowledgement DLL packet to return back to the remote transmitter. The TLP is eliminated. And when the DLL transmits a TLP, it retains a copy of the TLP. If it receives a negative acknowledgement for the TLP with this sequence number, it retransmits the TLP. When it receives an acknowledgement, or ACK, it discards the buffered TLP. So that's all about chapter 3. So the summary is we have discussed all about the computer components, the computer function, and then under computer function is the instruction fetch and execute, the interrupts, and the IO function. We also dealt with interconnection structures and then bus interconnection. We have also the point-to-point interconnect because bus interconnection has many disadvantages when there is already a large data. For the point-to-point interconnect, we have the QPI physical layer, QPI link layer, QPI routing layer, and QPI protocol layer. And then we also dealt with the PCI Express. So it has a similarity with QPI. So PCI physical and logical architecture, the PCIe physical layer, the PCIe transaction layer, and the PCIe data link layer. So we've already finished the discussion in chapter 3. So I hope you've learned something all about a top level view of the computer components. So I hope that you would like and subscribe to my YouTube channel. And of course, stay tuned for the next chapter on chapter 4. So thank you very much. Good day and stay safe.